In this module, we will put together everything that we have done so far and finally write and balance chemical equations. Chemical equations are like sentences. So they have all of these pieces that have to be present in order for the sentence to be complete or for the equation to be balanced. And what we're going to look at starting now is what those components are, what it means, and then how to go about making sure that an equation is balanced. So I have an example equation here, which is 2H2, and we've got a G in parentheses, plus O2 with a G in parentheses, turning into 2H2O with an L in parentheses. So this is a full balanced equation. Now, in general, the things that we have in this equation, we have some stuff on the left, an arrow, and then some stuff on the right. So the things on the left are called the reactants. Sometimes they're called the starting material, but as reactants, they are always on the left. And this might seem like a silly designation, but we will later look at reactions and talk about the reverse of the reaction or talk about the reaction moving in a different direction. We still always refer to the things on the left as reactants, and the things on the right are the products. So on the right, it will always be products. Okay, so and also I guess the arrow will also point from left to the right. The other things that you'll see in my balanced equation, we have some numbers in front of each of the chemicals that are in this equation. So I've got a 2 in front of the hydrogens. There's nothing in front of oxygen. That's actually like an implied 1, and a 2 in front of the water. The coefficients give the relative amounts in moles. So this is telling me that I need 2 moles of H2 to react with 1 mole of O2 to produce 2 moles of H2O. The last thing that we have in this balanced equation, and also the piece that is in some cases left out, so when you're writing a reaction, if you know the state, which is what that letter in parentheses means, then you should include it. There will be some reactions where having the state is required, and then there will be some reactions where it doesn't matter, or maybe we don't know, or we don't need to know, so it's fine. So the states that are listed here, you could probably guess most of them, and one we've already seen. So a G means that the compound is in the form of a gas. An S means that it's a solid. An L means that it's a liquid. An AQ means that it's an aqueous solution. Okay, let's now also take a closer look at the coefficients. For my 2H2, what I have here is that I've got an H2 molecule. So in my molecule of hydrogen gas, there are 2 hydrogens. And I have 2 of those molecules. That means that in total on this left side, I have 4 hydrogens. So 2 molecules where each molecule has 2 hydrogens means a total of 4 hydrogens. In my oxygen molecule, there are 2 oxygen atoms per molecule, and I just have 1 molecule. So I have 2 oxygens total on this left side. Now, the hydrogens and oxygens were in separate molecules, so I didn't need to add anything else up. If you were looking at this for equations where maybe hydrogen is present in multiple molecules, don't forget to account for all of the molecules. On the product side, I have 2 molecules of H2O. So 2 molecules, each molecule has 2 hydrogens, so I have a total of 4 hydrogens. And each molecule has 1 oxygen, so I have a total of 2 oxygens. And they match. I have 4 hydrogens and 2 oxygens on each side of this equation. And that's what it means for a reaction to be balanced. So these whole number coefficients, right, the numbers that are in front of the molecules, please don't use fractions, ensure that the reaction is balanced. And being balanced means that it has the same number of atoms of each type on both sides. And this is just a restatement of the law of conservation of mass. You cannot create or destroy mass, and in order to represent that, we need the same number of each type of element on each side. All right, of course, some examples, and combined with naming for these examples, we are going to write and balance the reaction where hydrochloric acid reacts with gaseous oxygen to produce liquid water and chlorine gas. A great first step here is just figuring out what each of these things means. So hydrochloric acid, I've got it written in words. What does that look like as a formula? Well, it is an acid, so it's an aqueous solution. The hydrochloric tells me that the hydrogen is just paired with a chloride. So HCl aqueous. It reacts with, so plus, gaseous oxygen. So O and with a G as a label. But you also have to note here and remember that oxygen was one of those Brinkelhoff elements, and that means that it needs to exist as O2. So O2 with a G. And then to produce means that I need to put an arrow because I'm done listing my reactants. So my products are liquid water, so H2O with an L, and chlorine gas, so Cl with a G after it, but chlorine is also a Brinkelhoff, so I need Cl2 gas. So I've taken all of my described in words, so the names of my compounds, I've converted them into formulas, I've put in all of the other information that I have so far, and I don't know, we could check to see if it's balanced. I'm sure we're not that lucky, but if we take a quick look, hydrochloric acid is the only thing that has a hydrogen in it. It has 1 hydrogen, and water has 2 hydrogens. So we're definitely not balanced here. We're going to have to put some coefficients in and see what happens. Now, strategically, there are different ways to go about this. Typically, you want to start with something that's maybe by itself, as long as it's not oxygen. Oxygen is usually never a good idea as the thing to start with. So let's start with something else and see where we end up. There are some reactions, like the combustion reactions we do next, where if you just do it in a specific order every time, you'll be fine, but it has a limited number of elements. So honestly, the first thing I might look at is the H2O or the Cl2, because for the hydrogen and the chlorine, because on the left I've got 1 hydrogen and 1 chlorine, and on the right I have 2 hydrogens and 2 chlorines. So I'm going to start by putting a 2 in front of my HCl, and I'm going to kind of like note it underneath the reaction in case it's not my final answer. So if I put a 2 in front of HCl, that would mean a 1 in front of H2O and a 1 in front of Cl2. And my hydrogens, chlorines, and hydrogens, chlorines are all balanced. So the thing that's left is oxygen. I have 1 oxygen on the right, and I have O2 on the left. Now, you can't balance this with a whole number. However, never fear, there is a method. You can temporarily put a fraction in. Now, you're not going to leave the fraction, but if I were to put a 1/2 in here, then my reaction would be balanced. And then I can look at these coefficients. I've only got one fraction. If I multiply by 2, I can get rid of that fraction. Everything will be a whole number, and I'll still be balanced. So that would give me 4 HCl, 1 O2, 2 H2O, and 2 Cl2. I can also go through and confirm that it's still balanced. So this would mean I have 4 hydrogen, 4 chlorine, and 2 oxygen on the left. And I have 4 hydrogen, 2 oxygen, and 4 chlorine on the right. So perfect, amazing, we love it. It's completely balanced. There are no fractions. I can't reduce my coefficients anymore. This looks great. For a combustion reaction, which is just, it's a really specific type of reaction. It is what happens when we burn things. We saw it for combustion analysis. Again, it's a reaction with oxygen gas, and the products are carbon dioxide gas and H2O gas. And this is something I would like you to know. So you will see problems that say this thing was combusted, write the balanced reaction. So you will need to know, because it said that it was combusted, that you need to react it with O2 gas and that your products are CO2 and H2O. For these reactions, you balance them in a specific order. And if you balance them in a specific order, you will not encounter issues. It's the most important thing, is to do them in order. Do carbon first, then hydrogen, then oxygen. So as an example, let's balance C5H12 gas being combusted. So it reacts with O2 gas, it produces CO2 gas and H2O, which is also a gas. Now, first I'm going to balance the carbons. On the left, I have 5 carbons. If I put a 5 in front of CO2, that would give me 5 carbons. Then hydrogen, on the left, I have 12 hydrogens. On the right, there are 2 hydrogens in every water. So if I put a 6 in front of my hydrogen, in front of water, I'll have 12 hydrogens. What this leaves me with, on the right, there are 10 oxygens in carbon dioxide and 6 oxygens in water. So 10 plus 6 is 16. I need 16 oxygens on the left, and I can accomplish that by putting an 8 in front of O2. Let's do another example, because we often combust things that have carbon, hydrogen, and oxygen in them. So let's take C6H12O6 solid and combust it. So react it with O2, you get CO2 gas and H2O gas. Wonderful. We're still going to balance everything in order. So 6 carbons on the left, I'm going to put a 6 in front of my CO2. 12 hydrogens on the left, I'm going to put a 6 in front of my H2O. For oxygen, I have 12 oxygens from carbon dioxide and 6 oxygens from water. So I need a total of 18 oxygens on the left. Out of the 18, 6 of them are already there in the C6H12O6. So 18 minus 6 is 12, so I'm only trying to make up 12 oxygens from the O2. So I will put a 6 in front of my O2, and now it is beautifully balanced. In combustion reactions, you will also encounter what we did in our example right before the combustion reactions, where everything was almost perfect, but you would have to put in a fraction. That method will also work perfectly for combustion reactions. So balance carbon, balance hydrogen. If you need to, put in a fraction for the oxygen, but then go back and multiply through all of the coefficients to get rid of your fraction.